Hi everyone, my name is Victoria Ryan. Here with me are my teammates Laura Bruno, Chelsea Doyle, and Lucas Pike. We're here today from Diamond Ship Designs to present to you our anchor handling tug supply AHTS vessel preliminary package design. So initially we were looking to design an ocean-going system which can tow, anchor, and transport supplies and passengers to and from offshore facilities. Specifically, it's going to have operations year-round in the Flemish Pass Basin. The Flemish Pass Basin is located approximately 500 kilometers off the east coast of Newfoundland and Labrador. Some key challenges that are faced in operations in this area include the distance from shore, the environmental conditions, as well as the extreme water depths.
So in term 7, we completed a detailed parametric study where we analyzed 6 different vessels. This semester we revisited the parametric study and we looked at another 6 vessels that are operating in the Flemish Pass area. We also did a significant amount of research this semester where we looked at different hull and bow forms, specifically which included the inverted bow, the axe bow, and the bulbous bow, to determine the best bow form. This semester, we also had the opportunity to meet with a lot of industry advisors to gain as much insight and feedback for a project as possible. Some of these included Statoil, Robert Allen, and Card, and the meeting with Statoil was particularly helpful because where they just finished their drilling program in the area this past summer, we got a lot of great information about the area and about what they're looking at for future operations. We also had the opportunity to do a vessel tour of the Atlantic Merlin, where we were able to gain a better visual understanding for certain design aspects of anchor handling tug supply vessels.
So here you can see some of our vessel particulars. We have a length overall of 98 meters, a beam of 24, and a design draft of 8 meters. You can also see here the displacement as well as the design speed. So this photo here shows our vessel, and here's some other views. You can see, based on our parametric study and research, a lot of what is incorporated here came from our concept study and now put into the preliminary design.
So just to get into some of the key features of our vessel that Victoria just showed you in the 3D model, we have an inverted bow design, which is good for improved seakeeping, as well as increased accommodation space, and it also increases hull efficiency. The next feature is, as our vessel is an anchor handling supply vessel, it is equipped with anchor handling equipment, most of which we selected from Rolls-Royce, as they have state-of-the-art technology, and as well as they emphasize minimal manual operations for their equipment, which is really important. The next feature is enclosed mooring in the bow of our vessel, which is really important for reducing ice buildup, as well as it reduces weathering of equipment. And lastly, just some other features that are included in our vessel are ice management, D&B clean deck design, which includes features such as a slope deck, as well as standby compliance, emergency response, firefighting capabilities, and ROV support.
Our vessel consists of the tank bottom, a second deck, first deck, decks A, B, C, D, and then finally at the top we have the bridge. So the bridge is outfitted with large windows all around for 360-degree view at all times during operations. Below that we have the accommodations for officers as well as crew. Our vessel has a complement of 77, so it was very important to have as much space for these people as possible to work and live. All cabins have the minimum required square footage for free space, as well as a dedicated unit head. Below this we have deck A, which includes the galley, a mess for the officers, as well as a common mess. We have a gym and other things for living. Below this we have our main deck, and here you can see some specific safety features such as the fast rescue craft hangar. Over on the other side we have an ROV hangar. There's also a hospital and the maximum working deck for operations. Here are just some different views.
And the tank arrangement was arranged in such a way to maximize tank capacities as well as account for appropriate machinery spaces. And as you can see here, there are ballast tanks arranged all along the sides in order to provide safety to the fuel oil and other contaminant substances in the tanks.
So here's our structural design of a midship section of the vessel. All calculations were conducted in accordance with ENGI's regulations, where first local ice loading was considered, or sort of local design loads, as well as the ice loading requirements, and then the global loadings were considered. You can see that the ice belt accounts for a significant portion of the side shell of the vessel. This is due to our extreme variation in cargo loading. And another note is that the section is mainly transversely framed with decks, longitudinal girders, and stringers for longitudinal strain. A weight estimate was conducted, which consisted of the structural weight, machinery weight, and outfit weight, with a total light ship weight of approximately 7,200 tons. Dead weight was also calculated, accounting for tank capacities and cargo on deck, which summed 6,300 tons.
So we also completed a stability analysis for the vessel. This included intact stability and intact stability with ice accretion. The first step in the stability analysis was to perform a weight estimate. The stability analysis was in compliance with Transport Canada's regulations. And for the stability analysis, we looked at 6 different loading conditions, which included light ship, light operating, 2 arrival, and 2 departure conditions. The analysis was performed in GHS, and for the intact stability, all cases were passed. We also looked at damage stability in our analysis. Based on a certain damage extent, we determined that there were 30 potential damage cases, all of which were analyzed in GHS. This damage stability analysis was also done in compliance with Transport Canada's regulations, and the same 6 loading conditions for intact stability were also analyzed. For the damage stability analysis, the majority of cases passed in GHS, and those that didn't were with respect to the minimum amount of freeboard for the vessel. And to improve this in the future, we would try to decrease our dead weight and tanks with ample capacity.
We also completed a stability analysis for our AHTS vessel with 2 main locations of interest, including the bridge and the accommodation decks. We obtained several results from this analysis, including heave, pitch, and roll RAOs, along with motion sickness incidents, as well as subjective magnitude. And here in the figure, you can see the locations of interest. So here is an example of motion sickness incidents on the bridge at head seas and a 4-meter characteristic wave height. And as you can see here, the MSI curve does not exceed the 8-hour limit for severe discomfort.
So the first step in our powering prediction was to develop an operational profile, which was created based on a parametric study and meetings with industry advisors. As you can see, the majority of the vessel's time will be spent in transit or conducting offshore operations, where it was determined most effective to have a direct drive diesel engine as opposed to a diesel electric. Prediction was to use max surf resistance, where we determined to achieve a design speed of 16 knots. Our effective power was 5,200 kilowatts. After accounting for all loss efficiencies, sea margin, and running the engines at 85% MCR, we determined the requirement would be 11,700 kilowatts. We're good. Relax. Stop stressing out. We're going to be fine. So
Gosh, you gotta do this in our presentation more like.
After considering a boiler pool of 180 tons, we also determined that the engine power requirement for that was 10,700 kilowatts, and therefore the driving factor in our engine selection was achieving a design speed of 16 knots. This led us to the decision of selecting 4 Rolls-Royce 3240L engines, producing a total brake engine power of 12,000 kilowatts. This provides our vessel with a boiler pool of 203 tons, exceeding our requirement.
We also completed a risk analysis, which included identifying hazards associated with common operations that the AHTS vessel will undergo, including navigation from St. John's to the Flemish Pass Basin, as well as anchor handling and towing operations, loading and offloading, along with oil recovery operations.
A cost analysis was conducted using Carriette method, where the cost associated with labor and material was considered. After accounting for 50% overhead on labor and 15% for additional anchor handling and towing equipment, we determined a total approximate cost of $186 million.
So to complete all those tasks we just mentioned, at the beginning of the preliminary design stage, we developed a Gantt chart, as you can see here, to lay out all tasks for each team member. So initially it was estimated that we would spend 462 hours on task, and then at the end of the term, it was determined that our actual hours spent on task were 787. With this, we met all project milestones, including the statement of requirements and work plan submission, along with our progress report, our poster, as well as our preliminary design package that we're presenting today. So overall, we are fairly satisfied with all results obtained from preliminary design, and we identified several areas of improvement to consider going forward into the detailed design stage. Thank you all for your time. Are there any questions?